you want it now. Yeah, so you need to, yeah, plus 1. You need to do some adjustment. You need to do some adjustment. I'm not saying this is the function. I'm saying this is how you can start, right? So what you can do is you only want it to be continuous, right? I'm not saying that Laplace u equal to that characteristic function is in the complement. So I can have it something over here, something nice over here, and I can make it 1 over here with using your modifiers. Modifier is 1 somewhere and 0 outside, C infinity function with compact support. You can use those functions. So try to do it.
I just wanted.
Yeah. Try to do it. That's what means, like one says it is possible to do this, it is possible to do that, it is possible. You can do it explicitly, no? So do that. So this part is correct for mod x greater than 1. Now I can take it slightly inside also. So that what happens is I can replace it by one function inside. Okay. I don't I needed something nice. Or I don't mind even corners, right? I don't mind corner because it is continuous function. I'm not asking differentiable at corner. So if I have this, okay, so this is 1, and so is this correct? So if I take if I take u1 plus 1, will I get my answer? What about u equal to u1 plus 1? Does it satisfy the required condition? It is continuous function, right? Huh?
Yes.
u1 plus 1 is a continuous function. Yes? u1 plus 1 is going to be a continuous function, right? Is it? Yeah. So I can define it to be u1 plus 1 for norm x greater than equal to 1, equal to 1 for norm x less than 1. So, is this correct? Because I'm not differentiating anything near the boundary. When I differentiate for norm x strictly greater than 1, my Laplacian is going to be 1. Yeah. And this is a continuous function. It works. Yeah. So you see it is not difficult, right? Every time one doesn't need to look for very difficult, complicated functions. So here you can see we started, and whatever we started with is still correct. So this is your solution to your obstacle problem. At least one solution, right? This identically one, and it is only continuous function. And the boundary here is going to be Lipschitz, right? You have a corner. You are cutting your parabola at norm x equal to, yeah. Are you sure? Yes? समझ में आया? तो यार चेक करो उसको, is it continuous? It is a continuous function and it satisfies. When you say something is a solution, it should satisfy the condition. That's all. And it satisfies. Laplacian u is equal to 1. Yeah. And it is 0 on B1. It is a continuous function. The The boundary you don't care, right? Boundary is not there. Yeah. So what about the second one? The second one should be a variation of this one because the second one is annulus. What happened? No.
The solution exists, it has to be unique.
Not necessary unless all your conditions are satisfied. Because in weak sense or it is harmonic, is it going to be harmonic? All those kind of things.
So that may be some, if by maximum principle uniqueness happens. Almost that.
Yeah, because it depends whether you're getting classical solutions. Yeah, that's what. Yeah, because if it is a weak solution, you have weak maximum principle. So already one is different. This is C2. This is differentiable.
No, the solution is not different.
I mean, that
The
harmonic part. Yeah. The solution here is only continuous. It's only continuous. So this one is obtained by changing that. Right? You still have Laplacian u is 0. So this is slightly different, right? You want it to be 0 outside the ball. You wanted the function to be 1, 0 on the boundary. So it is again going to be best is you look for radial solution. Right? So think about it quickly. Try to solve. You want gradient of u equal to 1. Yeah, you should do something for that. U is 1 here, and you have Laplace and u is equal to 0. So first thing is maybe you should try to find a function u which is harmonic in Br. Yeah, you try to find a function which is harmonic in Br. Then we can see because I want the function to be u or 1 in the interior of the ball. Maybe I adjust it later. Just find a harmonic function on just find a harmonic function in Br with the property that gradient u is 1. See, you are not having you have u equal to 0 and you have absolute value of u equal to 1 on boundary of Br. So you can still use your fundamental solution. Fundamental solution, right? Fundamental solution is what? 1 upon r power n minus 2. Constant times 1 upon r minus 2. Okay, it is harmonic. Okay. The good thing over here is that at the if you include origin, you will have Dirac mass there.
Yes, ma'am.
But you want to get rid of the Dirac mass part, and you're looking only for the continuous solution. So you can again cut out a unit wall, replace it by 1 here, and the remaining part you can take the half of it. Just see what about the gradient, absolute value of gradient. Then quickly. See, the absolute value of gradient. Now you think of it in terms of normal derivative, right? Because if I am having function which is function of r alone, then the gradient is what? In terms of r, how do you calculate the gradient? If u is a function of r alone, then gradient of u is what? You will have x by r. What is this gradient? So gradient is your d by dx1 of u, d by dx2 of u. And if your function is function of r, then d by dxi of u is equal to what? In terms of r, what will it be? Yeah, so what is it going to be? So it is xi upon r, right? So d by dxi is xi upon r times d by dr. Right? So instead of mod square, you can put mod u, mod gradient u, you can also consider norm of gradient u square is 1. So that you don't have that half appearing, so that you will not have problem about like xi upon r coming. So let's try to figure out. So what about the gradient? So you want this function to be a 0 on this boundary, right? So best is r is less than r. So 1 by r is greater than that. So this is a non-negative function. This is going to be 0 on the boundary. Laplacian of this is going to be 0 away from the origin. So you already got so many properties. What about the gradient? Find the gradient of this particular function. So you already have u equal to 0 on boundary of BR. You have u non-negative. Okay. You have Laplacian u equal to 0 in BR minus B1. You have so many properties you already found. Right? What about the gradient? And absolute value of that? Norm of x by r is 1. So you get it. So you have all three properties. Okay. Now comes the adjustment. Okay. Because this is the function you want in this part. Okay. I want it to be 1 here. Okay. So now let's see how we get it. We are to be equal to 1. Right? When r is equal to 1, you will have this number. Okay? You have to just match the continuity thing. Okay? So if I put it over u over here, 1 upon okay. What is happening? When I put norm x equal to 1, I am having 1 minus this. Whereas I want it to be equal to 1. How do you adjust?
Multiply the 1 minus 4.
Yeah. I cannot add or subtract because if I will add 1 upon r minus n minus 2, then it is gone. The only way is that I will multiply by that constant. Reciprocal of 1 minus 1 upon r minus 2. Then it becomes 1. And it will not affect any of these things. Okay? Except of course we will again have to see what happens to the gradient. If you multiply something, then the gradient is going to get affected. Right? So just see. Do you follow? So what will you do? Are you able to adjust the value?
I'm trying to find.
Yeah. So can you just do it? So when so suppose you take that. What happens when I take the gradient? Yeah. It should be possible. Yeah. I think it's not because the constant term when you take gradient, the constant term of the other one will go away. Just do it. Just do it.
I'm trying.
No, not you. I'm telling everyone. It's not a punishment for you.
What is C?
No, I'm saying that is that adjusting constant, right? So what? See, thing is, if I add 1 upon r minus 2, then my thing at this part is goes away. So my C, if I let me try and put it as reciprocal of 1 minus 1 upon r. Then it will be 1. I have made it continuous there, right? I'm looking for continuous solution, I made it continuous. So everything is satisfied. Whether norm of whether that is true. Huh?
What is desired you that we are?
Yes. That's all. Because we started with general harmonic fundamental solution. We slowly try to build up what changes we can make so that it fits our requirement. So now this function is 1 there. Okay? There are various ways. This function is 1, it is harmonic, okay? It is continuous. Yeah. And there may be other ways to do it. It is going to be 0 on the boundary of BR. Now my only problem is gradient of u, gradient of phi on the boundary. So I think there again you have to make some adjustment and like balance things out. Or you can put condition. C upon this is equal to 0 someplace and C upon this is equal to 1. And we get that. So you want to find C at mod x equal to R. Okay. You need to have that kind of balance. Or whether whatever we found works. So will you try to fix it? Yes. Let me. Now, this one is similar. I think this one is easier than that one relatively because you don't have annulus. You have you have condition on u. Okay. So let me do a little bit of Harnack inequality result. Not much. Then we can do that. Yes. I will do that. I will prove that. Do you want to spend 15 minutes more doing this one? Yeah, it's good. Huh?
A little more.
Yeah. No, but it is this one is adjustment of the constant. You want to see?
This way. Even when C should be
You're not getting?
no, I'm getting subtraction in the this side differentiate. You take mod square of this. Only one on boundary. So this will be 1. Norm x square will be r
R
square.
square. Yes.
So this is r square plus 2 1 minus a.
Yes.
And this factor is coming in the differentiation.
Yes.
So this into c should be 1.
Yes.
So c should be reciprocal.
Yes.
But my point is first 2 minus a should not come in the denominator.
What?
Because
N is greater than 3. N is greater than 3, greater than equal to 3. Otherwise it is log.
Yeah.
That's what. So you have condition. But that constant C works for both. It should be such that it should be equal to 1 here and it should be distant. You have to choose.
More gradient.
Yeah, but you also have that.
And Laplacian.
No, Laplacian is not difficult. You also have this part that
That is
Yeah,
I differentiated C times that.
yeah, that's what. So then once you have chosen C, so you have to choose C that is equal to 1 as well as this. There is something more. Oh, just check. There is something more. Just check. You want to try this one? Yeah, you can spend time finding out constant or maybe splitting it up more. Split it up more. Okay, you try to adjust the inner boundary, then continue with the same function. You can take C infinity function with compact support. So so which is yeah. So if you can do some kind of adjustment with that and try to do it, because maybe the same constant may not work for the inner boundary and outer boundary. So it's good to see that you can, but maybe tomorrow when you come, at least tell me. I'm curious. So what about this one? So this is in B complement, right?
Yes.
So we found a solution, right? Somewhere. That one. Laplacian u equal to characteristic function of u greater than 0. Yeah, what was that? That was like, and it was 1 on B1. Yeah. So instead of yeah, I think this one. So you say what are its properties? So like P was this, that is the property that Laplacian of u1 is equal to 1 and u1 equal to 0 on boundary of b1. In fact, you don't need that.
1 on the
Yeah, it is 1 on b1.
1 on the boundary also.
So this is the other way around, right?
So you can just divide by lambda.
Yeah. And this one you
Instead of writing 2n.
yes. No, it's not that. You can scale. You can scale.
Scaling will not give 1 on the boundary. Scaling will not give 1 on the
No, you will have to adjust. See, this one is opposite of that. This one is the Laplacian of u1 is equal to 1 on b1 complement.
This is also.
Right? So this is so what I'm saying is you can use this function. Now, if I put u1 of alpha x, it comes out as alpha square. right? Laplacian of u1 of alpha x will come out as alpha square. So if I take alpha square to be equal to lambda, then I will get using this function.
Scaling by 1 by root lambda.
Yes,
Huh?
yes, yes, yes. That's what I'm saying it other way down. Okay, so if I take v of alpha x, then Laplacian of phi is equal to alpha square Laplacian of v of alpha x, right? Then what do you get? Which is equal to so if I put alpha square equal to 1 by square root lambda, then I would get. So if I take phi of x is equal to v of x upon root lambda, then I will get Laplacian of phi is equal to 1 upon root lambda, 1 upon lambda on v1 complement. Right? I will still get the function to be equal to 1 on boundary of d1. In fact, it is 1 everywhere if I use this function. Yes? They are lost. So thing is, let me let us try. So this was the nice function which we got, right? Laplacian of this is equal to 0. If I add 1, it becomes 1. I can add 1 upon lambda directly. If I add 1 upon lambda, it becomes just 1 upon lambda, Laplacian of that. Okay? It is going to be 1 then. So let's see how you try it. Because if my u is already of this form, then I am getting condition on my norm. Okay, let us look at this function first. Laplacian of u1 is
1 upon
1. That is what we are working. It is equal to 0 on. So in fact you don't even need this. This function will give 1 on boundary of d1.
Yes.
Yes?
1 by 2.
1 by 2 and 3.
No.
Minus
You have to add 2
Add 1.
Add 2n.
No, I want it to be 1 on boundary of d1. So you have to add c. You add some constant so that it becomes 1. It is 1 out. And then you want it to be such that put conditions on norm x square. So here so if it is just norm x square, forget all those constants first. And if it is just norm x square, then on 0 on norm x square less than lambda. Norm x square less than lambda, you want Laplacian u equal to 1 upon lambda. Right? Yeah, if you are just considering u to be norm x square, Laplacian of you want Laplacian of u to be equal to 1 by lambda for norm x square less than lambda. Right? That's what it means. So I want it to be if you think it like that, then you will be able to do it. Because Laplacian will be what? Laplacian will be 2. You just put norm x square, right? And instead of just norm x square, you want norm x square divided by lambda. Norm x square divided by lambda. Yeah, Laplacian 1 by lambda will come out. Okay, but you want norm of uh, for norm x square upon lambda less than lambda, it means norm x is less than lambda square. Norm x is less than lambda. So that's correct. That's correct. Correct. So I think you can try. You want it to be 0 outside because it is characteristic function of this set, right? So you want your angular region. So you want in mod x greater than lambda, you want your function to be zero. Yeah, you want it to be 0 here. Here you want it to be 1 upon root lambda, and here you want it to be 1 on this particular function. So you try playing with this one. Okay. Some adjustment at that boundary and so on. You may have to use cutoff functions to get some kind of smoothness or put 0, put distance between that. So try to figure it. So maybe let me do the highlight to the quality. Yeah, so I will send you when I send you notes, there are some typos because I corrected yesterday in that about dual specs of W12. Yeah, so there was like in that lecture notes, there are some typos are there. So just ignore. Yeah, and at least let me write few things. So the Harnack inequality, as we have already seen, it gives you relation between the supremum of the function and the infimum of the function, and as we have seen many times that it means that the functions cannot become too large or too small. Okay, they are kind of balanced for. So this notation means compact subset of E. So at least it is nice to know sometimes, like when we are looking for tools to solve certain problems, we wonder what to use. Okay, so sometimes if somebody has told us, it is easier. So Harnack inequality is can be used to prove, like it appears many times, but this is where one can think of this as a tool. And we have already seen in Hendrik's class couple of times where it appears. So this is higher C alpha regularity of for alpha greater than 0. Yeah, that is what we have seen, right? Because I said this will give you your Arzelà-Ascoli type, uniform boundedness. If the function is bounded from below, this says that supremum is uniformly bounded, and then you can take limit and get the conclusion. Second, Liouville's theorem. Okay. You can use it to prove Liouville's theorem. A bounded harmonic function is constant. You have to try to prove Liouville's theorem assuming this. So of course, if you want to say an entire domain, right? And so when you talk of bounded set obviously it is going to be bounded. But if you are talking of, when you talk of Liouville's theorem, it is going to be an entire function. So Laplace on Rn, yes, on Rn. So how do you do it? What do you do in your complex analysis? Remember?
Maximum principle.
Yeah, so you have maximum principle here as well, right? But we are trying to use Harnack's inequality. So suppose it is not constant, then its infimum is different from its supremum, and then you can try and do this over increasing balls. Just try to see how you get it. It is a good exercise without knowing, without using maximum principle. And that's what I had said, that it is equivalent to your maximum principle gives this. Like all these, some of the properties are interrelated. So this is again what we have seen. So if Laplacian u equal to 0 in ball minus origin and ux is over mod x power 2 minus n, and v1 is the removal singularity. If you have u going to 0 faster than your fundamental solution, right, then it is controlled. So you can put it as 0. But of course you still have to check that it is going to be harmonic in neighborhood of origin as well. Okay, you can use your the fact that a harmonic function is analytic function. Yeah. So this is so as I said, some kind of uniformity, not too much of fluctuations are possible if you are looking at harmonic function. So here you have a propagation of smallness. If u is small in subset of omega, then in simple language, right? Because you can always say that the supremum is comparable. Because remember, after that I had also written if I have two different x and y's, then there are constants such that you can compare ux and uy. Right? That is what. So it is not just about supremum and infimum, but in any set, as far as you are away from your boundary of the domain, you can compare the values for that fixed C. Okay? And that C depends only on the set, on the name. So let us try to prove it. Proof is not difficult, and even for this purpose, if you write it down for balls, the Harnack's inequality, if you write it down for balls, it gives you explicit values of C, so that you can control. And most of the times, whenever you're doing things locally, once you know it for balls, it's more than enough, right? So that is what I will write down. So you take, this is your omega, x is a given point. Okay. So what do we know for x belong to omega? What happened? For x belong to omega, you can write the mean value property. Okay. What do you have? You have this is going to be 1 upon. So let me write it as u of x is u of y dy dx. Right? So here, what am I doing? See, I want to have this kind of estimate, right? When you are taking supremum over a set, I'm going to vary it over all values x in that. Okay. Then when I take infimum also, I'm going to vary it over all values of this. So basically, when I start with a point, I want to relate it to some other point. Okay, you have followed what I am saying? Let me go back to that. Remember, this is what I had written. Yeah, because any at any other point, any point, it is going to be less than equal to this, and at the same point, it is going to be greater than equal to this, right? So basically, what I have to do is I have to get two different value of the function at two different points in the picture. Now, what I know is the value of the function at one point. I can write it as this particular average. Then, what I can use is that this ball, I can assume it to be contained in a larger ball, right? And q is positive, that is why you use. So this is less than equal to integral over. So x tilde u of y dy. Okay, I can do that. What am I doing? I am taking integral over a smaller ball, and u is positive. If I take integral over a bigger set, it is going to be bigger than that. I am not changing the first term. Right? So of course this r, let me change it. So I can make it 2 times r. Right? I can make it 2 times r, and in fact I can do it better. Huh? Yeah. I just have to. So this is contained in ball of radius 2r, which is centered at a point x tilde. Only thing is now I want to average it with respect to ball of radius x tilde. Okay. So here I think we did it twice. Added, multiply and subtract. But this is nothing but u of x tilde. Okay. So what I have shown, u of x is less than equal to this ratio. But this ratio kind of okay, right? Because what is this? How do you find out? How do you find out volume of radius 2r? It is going to be volume of unit ball multiplied by 2r power n. This is going to be volume of unit ball multiplied by r power n. That's all, right? So you have found basically a relation between ux and ux theta. So here in the proof which is there in the notes, just to avoid like if we have taken ball of radius 3r, because maybe I think this should be enough. You can do it in 2 steps. Anything to say? So then what happens? You take infimum, supremum over x and infimum over y, and you will get it. That's what. So of course this is relative only to a ball. So if you are taking a compact set K, you cover it by finitely many balls, and you will find a constant which is going to depend on your compact set. But the basic idea of the proof is just application of your mean value property. That is all. Okay. Just think whether this is okay. So I just want to point out something, because this is something which we don't usually think. He Henrik mentioned some result about that particular example which holds even if no PDE is not satisfied, right? The function does not satisfy any PDE, still that certain result holds. Okay. So here we have similar. It's just an observation that for C alpha functions, Harnack inequality holds. Okay. What do I mean by that? So C alpha functions are Holder continuous functions, right? So what do I have? So this suppose this implies mod of ux minus u1 is less than c prime mod x minus y power alpha. So for this is true for all x, y in the set, right? So of course we are looking at compact set, right? Whenever we talk of Harnack inequality, we are looking at compact sets, and also we are saying that here these functions are continuous. So what we do is we also assume u greater than 0. We want it to be Harnack inequality is for non-negative, positive functions. Otherwise, it doesn't make sense. Okay. So I used it is positive over there. Yeah? So let n equal to infimum of u, which is achieved at a point ux naught, we are in a compact set, restricted to compact set. Then you define v of x to be u of x minus
In K.
u of x naught. Okay. Then v is also Holder continuous. U is Holder continuous implies v is Holder continuous. Then v belongs to C alpha. Also v of x is same as vx minus v of x0. v of x0 is 0. Here, I defined it. If I put v of x equal, and this is infimum, so v is still non-negative. V is also a positive function. This is 0. And if I use Holder continuity, what do I get? This is less than c times mod x minus x naught power alpha. Okay, and this I can less than equal to c times diameter of k. Right? So what do I get? The v of x is less than equal to c times diameter of the compact set k. Okay. So now if I substitute this, I get the u of x plus m plus u of x naught. Right? So of course there is some kind of, so if I let this to be equal to m, so then this is less than equal to c times diameter of k upon m plus 1 times m, that is u of x naught. Okay. Yes. Yes. The only one thing which I am having question about is that particular constant does depend on u. It is not just a constant which depends on k alone. It depends on u. So it is not harmonic in that sense. But it is still similar. It allows you to compare the supremum and infimum of the function. And there is there is no PD. It's just straightforward. So I think I will stop it here. It's T. It's clear, right? No, so here in fact like one of course I manipulated it for points just nearby, right? But what I could have done is I could have started by 1x over here, 1x tilde over here, and try to compare these at two different positions. But that's one can just iterate and do it. Okay. So this is easier to see. If I have one ball here, then I can take a bigger ball over here which contains it, and I get it. If things are far away, then you will have to catch up. this way. So that is why you will get your constant which depends on the set. There is no function appearing over here. There you have that function which appears over here. So this is what is finite inequality. I suggest after the T, we'll try to solve that problem. He wants us to solve that problem. If function is monotonic everywhere, then it has to be. It should be only one dimensional.
Okay.
There is no problem.
It's not monotonic in all
Monotonic in
directions.
all directions. And so we don't need to do it in Rn, right? We should do it only in R2 or R3. Let us do it in R2 and R3 and see, because it looks nice and simple, right? So we can try to solve it. We can try to do it after it.
Just depend on directions.
In one direction.
So yeah. So
One degree of
you wrote that h of x times s squared